Alright, this is 14.8, which is change of variables in double integrals, which can be thought of in a way as like a fancy substitution. Let's say substitution with two variables is a helpful way of thinking about what it looks like, of what it means. Right? So before going into this, I just want to look back at two examples from Calc 1 that'll help us see what's about to happen, because a lot of similar things will come up. So consider these two Calc 1 problems. So A be the integral from 0 to 1 of the square root of 2x plus 1 dx. And B will be the integral from 0 to 1 of the square root of 1 minus x squared. So both of these are done with substitutions. The substitutions are somewhat different. The one on the left is a classic substitution. The one on the right is a trig substitution. So I'll write down the substitution for both so we can see how they're similar and how they're a little bit different. So this is what we would do in each. In A, we put u equals 2x plus 1. So then we change the limits of integration. Then x equals 0. This becomes u equals 1. And x equals 1. This becomes u equals 3. And then du becomes 2 dx. So dx becomes 1/2 du. So then when all is said and done, this integral gets changed into a new integral, 1 to 3 of the square root of u 1/2 du. And then you just charge ahead, go from there. In B, a little bit different, we'd put x equals sine of u. So then again, we need to change the limits of integration. And x equals 0. This is a little bit different because when x equals 0, 0 is sine u. So u is 0. And x equals 1. 1 is sine u. And u is pi over 2. So then the dx is a bit easier because dx is just cosine u du. So at the end of the day, this integral, this becomes the integral from 0 to pi over 2 of the square root of 1 minus sine squared u times cosine u du. And then that simplifies and we go from there. Not going to worry about that right now. Right? The point that you see is like a similar thing happened in all the cases, right? Like in both cases we had a substitution. In the first case we had a u equals right here. The second case we had an x equals, but they're both changing variables. We're changing the variable from an x to a u. And then in both cases, notice three things changed. In other words, let's be specific. In both cases, once we chose the substitution, three things change. Those three things are the integrand. That's the thing inside the integral sign. 2, the dx is replaced. And 3, the limits of integration. So for a double integral, we're basically doing the same thing. We're starting off with an integral. We're going to make a substitution. There'll be two variables here. And after we make that substitution, three things will change. So let's see how this all pans out. Right? So 2. Method for two variables. So here the situation is as follows. we've got a double integral. It looks like this. Whoa, that kind of came out kind of weird. Integral over r of f of x, y, dA. So we make a substitution. Now this can be done one of two ways. So just like on the left, we could have a u equals, or we could have an x equals. So here we have two variables, so it's a little bit more mixed up, but the idea is the same. Right, so there are two possibilities. And which one we choose will become evident as we go through the examples. So two ways. So either we could do u equals and v equals. Those would be functions of x and y. Or we could do x equals and y equals, and those would be functions of u and v. So just like before, one of these two ways could come up, and it'll depend upon the problem that we're doing. So once we do that, a couple of things change. Well, three things, just like before. So, one, the integrand changes. And that'll change according to the substitution, as we'll see. That's actually usually not the sneaky part. So two, I'm going to do these slightly different order from before. So the r, which is in the xy plane, becomes a new region. S, which is in the uv plane. And three, this is the tricky bit. It's not tricky to do, it's just sort of a bit odd. Is that the dA gets replaced. By what's called the Jacobian of the substitution. I'll just say the Jacobian. Okay. And the Jacobian can be calculated one of two ways. Right. Sorry, I totally misspoke. Let me back this up a second. The dA gets replaced by the absolute value of the Jacobian times dA, where this Jacobian can be calculated two different ways. One of two ways, really. So we have a choice, and the choice, how we choose, will become clear. So let me write this either this way. So the Jacobian, so the formal definition is it's the determinant of the matrix partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. Or it can be calculated as 1 divided by the determinant of the different matrix. If you've had linear algebra, you'll recognize this as a matrix inverse, but this is 1 divided by the determinant of partial u, partial x, partial u, partial y, partial v, partial x, partial v, partial y. Now, if you want to know which one you use, it's actually pretty easy to see. So here's the deal. If you look up to our substitution methods, right, on the left we had this one right here. I'm going to circle in green. Here we have u and v equals. And so it makes more sense in that case to find the partials of u and the partials of v. So in that case, you would use this second one down here. On the other hand, if we did this substitution up here, then you have x and y equals. Then it makes more sense to find the partials of x and y, in which case you would use the first version. So they kind of go hand in hand. So once you make the decision about the substitution, that tells you which Jacobian to use. Then you find the Jacobian, find the absolute value, change everything else, see how that works out. So I'm going to clear the screen now, and I'm going to go through an example in full from start to finish. It's sort of a classic example, and then I'll do some more examples in an addendum. But for right now, sort of just digest the right-hand side before I erase it. We have a double integral, we make a substitution, three things change, and then we get a brand new integral. And the integral, as you'll see, will become significantly easier to evaluate. So here we go. So here is an example. We're going to calculate the double integral over r of x dA. Now before I draw r, you might wonder like why a substitution would happen, because this integral is just an x. So you might say like, well, what's tricky about this? So what makes this problem tricky is the r. And it's very often the case that when we do substitutions in two variables, it's to change the region to something nicer. So what I'll do is I'll draw the region for you. It's going to be a parallelogram. It's going to have a line at y equals 1/2 x, a line at y equals 1/2 x plus 2, a line at y equals 2 minus x, and a line at y equals 4 minus x. And the r is going to be that region. So this region in here is not very pleasant. Like, it's not easy to do as vertically simple, horizontally simple, or absolutely not in polar. So r is not nice in vertically simple, horizontally simple, or polar. So what we'll do is we'll make a substitution that will change r into something nice. So the way to see that for this particular example is, first I'm going to rewrite the four lines. I'm going to rewrite the equations of the lines that bound r. Right, so first, rewrite the lines. So in the order that we gave them, right, first we had y equals 1/2 x. So I'm going to multiply by 2 and subtract the x. So we get 2y minus x is 0. For the second one, 1/2 x plus 2. Ditto, I'm going to multiply by 2 and subtract the x. So we get 2y minus x equals 2. Notice those are very similar, right? They both have a 2y minus x on the left-hand side. For the next one, y equals 2 minus x. I'm going to just add an x to both sides. So x plus y equals 2. And ditto with this last one, x plus y equals 4. So what you see now is that these are sort of in categories, like they group together. These two are similar, these two are similar. So what they do is they suggest a substitution. So let's make a substitution. We'll substitute u will be 2y minus x, and v will be x plus y. So when we do that, these four lines change to four significantly nicer lines, right? So this changes our lines to the following. So I'll list them in the exact same order. So the first line becomes u equals 0. Second becomes u equals 2. V equals 2, and V equals 4. These four lines form a really nice region in the UV plane. All right, so you can probably see what's coming is in the UV plane. Let me draw this in blue as well. Now, I made the u-axis the horizontal axis. That's totally irrelevant. Choose whichever you like. They're arbitrary letters, but it's pretty traditional to make u the horizontal axis. So u equals 0 is vertical right here. U equals 2 is right here. V equals 2. And V equals 4. And this guy is now our S. This is significantly nicer This should make us very happy. That is easy to iterate. It's vertically simple, it's horizontally simple, it's great. So that's what our R becomes. And then we go, well, great, well, now I just have to change everything else, right? So we now know S. So what about the other two things? Let's first look at the Jacobian, right? So since our substitution was of the form, so if you look back, it was U equals and V equals. Right? It makes sense to use the version of the Jacobian that goes along with it, right? So what we do is we'll do the Jacobian, I'll just write Jack. This is 1 divided by the determinant of partial U, partial X, partial U, partial Y, partial V, partial X, partial V, partial Y. This is 1 divided by, so partial U, partial X is -1, partial U, partial Y is 2, and then 1 and 1, these other twos. This is 1 divided by, so this determinant is 1 times -1 minus 1 times 2, so that's -3. So this is -1/3. That's great, we know the Jacobian. Last thing we need to do is the integrand. Right, so the integrand is X. So then we need to know, what does X equal? That's not obvious, right? We have a substitution that says U equals and V equals. We need to know what X equals. So we'll have to work that out. So we'll have to go back to the substitution and figure it out. So what we can do is, if you go back to this substitution over here, lower left, what we'll do is I'm going to take the first one and I'm going to subtract 2 of the second ones. Right, so take the substitution. So I'm basically solving for X in that thing. So I could, if I added those equations, I would cancel the X. That's not what I want. I want to cancel the Y's. So actually what we can do is we can negate the first one. So let me rewrite it. Actually, we just rewrite both. So this first one, I'm going to negate it. And the second one, I'm going to double it. I'm going to add these two. And you can do this a variety of ways. As long as you get the X eventually, you're good. So this gives us -U plus 2V. The Y's cancel, and we're left with a 3X. So this tells us that X is -1/3 U plus 2/3 V. So we're good. We can write down an answer now, right? So our original integral becomes an integral over S. The X gets replaced by what we just calculated. The dA gets replaced by the absolute value of the Jacobian times a new dA. Right, so before we go any further, just to reiterate, right here, we just substituted what we did. This guy, this is the absolute value of the Jacobian. So when we've done that, then we can iterate it. So then we go, and now we're sort of out of this section, and then we notice that S is vertically simple. So the U's go from 0 to 2, the V's go from 2 to 4. We have all this stuff in the middle. And then we have D, V, D, U, and that's the end. Then we just evaluate it. So take a look at that, see if that all makes sense. What I'll do is I'm going to end the section here, and then I'll do a few more examples in addendums so we can separate them and do them one at a time. And we'll see some other things that come up. Like we'll do another example where maybe the substitution doesn't need to be fiddled with at the end, or maybe the Jacobian needs to be done a different way. Maybe we do it for a different reason. So we can tease those out in the examples, but this is a really good example because it's like a nice substitution. It's an easy Jacobian. Finding the integrand, solving for x is not trivial, but not difficult. And we get a really nice integral at the end. So I will stop there.